Bismillah ar-Rahman ar-Rahim. This video is about contraction mapping theorem. So we have a Banach space, a complete and normed vector space. Let's call it big X. And we have a mapping T from X to X. And this mapping is a contraction mapping. This means that for every X and Y in big X, suppose that we apply the mapping T to X and we apply to Y. Then the norm of Tx minus Ty is less than or equal to alpha times the norm of x minus y, and alpha is a non-negative real number that is strictly less than 1. So alpha is in the interval from 0 to 1, but it is strictly less than 1. So this means that this norm is strictly less than this norm, and hence the name contraction. Suppose that we have an iterative algorithm. Xn plus 1 is equal to t applied to x of n. So we initialize, we have x of 0, and then we apply t. We get x of 1, which is t x of 0. And then we apply t again to x of 1. We get x of 2, which is t of x of 1. Then we apply t again to get x of 3, which is t of x2, and so forth. Now we have a sequence. We have a sequence of points in this Banach space. x0, x1, x2, and so on. The question is, does this sequence converge? If yes, what is the limit, and is the limit unique? Because this domain of the mapping T is complete, this means that every Cauchy sequence in big X converges. So if we want to show that this sequence converges, we can show that it is a Cauchy sequence. Let's recall that this sequence is a Cauchy sequence if for every epsilon that is strictly positive, there exists a big V such that for every n and m greater than or equal to big V, we have that the norm of xn minus xm is less than epsilon. So it means that the elements of this sequence are getting closer and closer to one another. There is always a threshold such that if we have the two indices n and m are above that threshold, then the norm of xn minus xm is less than any arbitrary positive number epsilon. Let's start by investigating the norm of xk minus 1. This is the norm. Xk is t of xk minus 1, and xk minus 1 is t of x of k minus 2. Because this is a contraction mapping, this is less than or equal to alpha, a non-negative real number strictly less than 1, times the norm of x of k minus 1 minus x of k minus 2. But this is t of x of k minus 2 minus t of x of k minus 3. Because this is a contraction mapping, the norm will be less than or equal to alpha, and then there is another alpha, so we have alpha squared, and then the norm of x of k minus 2 minus x of k minus 3. We can keep doing this, and the idea is that the norm of x of k minus x of k minus 1 is less than or equal to alpha to the power k minus 1 times the norm of x of 1 minus x of 0. Let's try to show that this sequence is a Cauchy sequence. So let A be the maximum of m comma n, and B is the minimum of m comma n. We want to study the norm of xm minus xn. We want to show that this norm can be made arbitrarily small by choosing m and n to be large enough. So this norm is the norm of xa minus xb. And the idea now is to subtract xa minus 1 and add x of a minus 1. So I will have xa minus xa minus 1 plus xa minus 1 minus xb. Now apply the triangle inequality. We will treat this as a vector and this as a vector. So we have this norm is less than or equal to the norm of xa minus xa minus 1 plus the norm of xa minus 1 minus xb. We have this result here. So this norm is less than or equal to alpha to the power a minus 1 times the norm of x1 minus x of 0. And then here in this norm, we subtract x of a minus 2 and we add it. Again, apply the triangle inequality, treating this as a vector and this as a vector. This term, just copy paste. And then this norm by the triangle inequality is less than or equal to the norm of xa minus 1 minus xa minus 2. plus the norm of xa minus 2 minus xb. We have our result here. Now k is equal to a minus 1. So we have a bound which will be alpha to the power a minus 2 times this norm here. So this is less than or equal to alpha a minus 1, then the norm of x1 minus x0 plus alpha of a minus 2, then the norm of x1 minus x0. And then here we subtract xa minus 3 and add xa minus 3. Then we apply the triangle inequality and so forth. What will we get? We keep doing this till we get a norm that is the norm of x of b plus 1 minus x of b. So the last term that we will get will be, again, a norm xb plus 1 minus xb. So this will be upper bounded by alpha to the power b times the norm of x1 minus x0, which means that x of m minus x of n is less than or equal to the norm of x of 1 minus x of 0. And then we have alpha to the power a minus 1 plus alpha to the power a minus 2. And we go all the way to alpha to the power b. Let's write this bracket as a summation. So this is the norm of x1 minus x of 0. We have summation. J is from b to a minus 1 of alpha to the power j. This is upper bounded by the norm of x of 1 minus x of 0. And then we can just take this summation to infinity, alpha to the power j. This is a convergent geometric series because alpha is strictly less than 1. So this summation here is equal to alpha to the power b divided by 1 minus alpha. Can we make this upper bound arbitrarily small, less than any given positive epsilon? Yes. Now, if alpha is exactly equal to 0, well, this is 0, and 0 is less than epsilon. If alpha is strictly between 0 and 1, then we have, so now alpha is between 0 and 1. Alpha to the power b is less than epsilon times 1 minus alpha divided by the norm of x1 minus x of 0. We can take the logarithm of both sides. So we have b, which recall is the minimum of m and n. And we have here log of alpha, which is a negative number because alpha is between 0 and 1. And this is less than, and then we take the logarithm of this one. Taking the logarithm is not problematic because logarithm of z is monotonically increasing. Now divide both sides by log alpha, which is a negative number. So we need the minimum of m and n, which is b, to be greater than log of epsilon times 1 minus alpha divided by the norm of x1 minus x of 0. And this log is divided by log of alpha. So yes, for any given epsilon, there is a value that if m and n exceed this value, then the norm of xm minus xn can be made less than epsilon. And this is true for any positive epsilon. So the conclusion is that, yes, x of n is a Cauchy sequence, and hence it converges. So the sequence x of n converges, and limit n tends to infinity, x of n, let's say that this is equal to x star. Now we want to show that x star is a fixed point of the contraction mapping T. So x star is equal to T of x star. If you apply T to x star, you get x star itself. So is this true? Take the norm of x star minus T of x star. X star is the limit of the sequence. The sequence was proven to converge, and so there is a limit. We called this limit x star, and now we are investigating the norm of x star minus T of x star. Subtract and add x of n. Apply the triangle inequality. Treat this as a vector and this as a vector. So by the triangle inequality, this norm is less than or equal to the norm of x star minus xn plus the norm of xn minus T of x star. And I will write it xn minus T of x star. Then I subtract here T of xn and add T of xn. We can apply the triangle inequality again, treating this as a vector and this as a vector. So this is less than or equal to the norm of x star minus xn plus the norm of xn minus T of xn. And then we have the norm of T of xn minus T of x star. For this term, T of xn is xn plus 1. So this is equal to the norm of x of n plus 1 minus xn. We have an inequality for this. So we have x of n plus 1 minus x of n. If we take the norm of this, we get an upper bound will be alpha to the power n times this norm of x1 minus x0. This is less than or equal to alpha to the power n, and then we have the norm of x1 minus x0. What about this? From the properties of the contraction mapping T, this is less than or equal to alpha, and then we have the norm of x star minus x of n. Our upper bound is alpha to the power n times the norm of x1 minus x0 plus 1 plus alpha, and then we have the norm of x star minus xn. Here we have the norm of x star minus t of x star. Take the limit of both sides as n tends to infinity. Now the left-hand side is not a function of n. So when we take the limit as n tends to infinity, this remains as is. Less than or equal to the limit as n tends to infinity, we have alpha to the n, the norm of x1 minus x of 0 plus 1 plus alpha, and then the norm of x star minus xn. Because alpha is strictly less than 1, this term here tends to 0 as n tends to infinity. What about this other norm? We have, as n tends to infinity, xn converging to x star. So this means that for every epsilon that is greater than 0, there is some big N, such that for every n greater than or equal to big N, we have that the norm of xn minus x star is less than epsilon. And this is equivalent to limit n tends to infinity of the norm of xn minus x star equal to 0, because this norm can be made arbitrarily small by making n large enough. So this limit also will go to 0 as n tends to infinity. We have now that the norm of x star minus t of x star, and this is a non-negative quantity less than or equal to 0. The norm is exactly equal to 0. If the norm is equal to 0, then here we have the all 0 vector, and it must be the case that x star is equal to t of x star. So the limit point of the sequence is a fixed point of the contraction mapping T. Suppose that limit n tends to infinity of x of n is x star, and the limit n tends to infinity of x of n is equal to y star. Can y star be distinct from x star? Or they must be equal and we have a unique limit? If we have this statement here, then as shown, x star is equal to t of x star. And if this is true, then y star is equal to t of y star. Now let's examine the norm of x star minus y star. What is x star? It is equal to t of x star. And what is y star? It is equal to t of y star. T is a contraction mapping, so this is strictly less than or equal to alpha times the norm of x star minus y star. And alpha is strictly less than 1. If x star is not equal to y star, then this norm is strictly positive. But then what we have is that this norm, which is upper bounded by alpha times itself, and alpha is strictly less than 1, then this will be strictly less than itself, which is impossible. So the only possibility is that this norm is equal to 0, and so x star is equal to y star. We have a unique limit. As an example, for applying the contraction mapping theorem, let's use it to prove the following result. We have a function g from R to R. It is a C1 function. G is differentiable, and the first derivative is a continuous function. The first derivative of g evaluated at point A is not equal to 0. There exist neighborhoods u from A minus delta to A plus delta, and delta is a positive real number. So that's a neighborhood of A. And then there is the neighborhood or interval V from g of A minus eta to g of A plus eta. That's a neighborhood of g of A, and eta is a positive real number, such that if we pick z star in big V and carry out the following iterations, x sub 0 is A, and x of n plus 1 is equal to x of n minus, we have a ratio here in the numerator, we have g of x of n minus z star, that point that we choose in interval V. And in the denominator, we have the first derivative of g evaluated at A, and this by assumption is non-zero. The claim is that if we carry out those iterations, the sequence xn converges to a unique point x star, such that g of x star is equal to z star. In other words, we are trying to solve the following equation. G of x is equal to z star. We are interested in obtaining a value of x such that g of x is equal to x star. And we do this iteratively. We initialize the sequence x using x of 0 equal to a. Then we carry out those iterations. Note that z star is chosen such that it is in the neighborhood of g of a. It is close enough to g of a. And the solution to this equation will be in a neighborhood of a. The first derivative of g is continuous. From the definition of continuity, for every epsilon greater than 0, there must be a delta such that for all x, satisfying that the distance between x and a is less than or equal to delta, we have that the difference between the first derivative evaluated at x and the first derivative evaluated at a, the magnitude of this difference is less than epsilon. By choosing x to be close enough to a, the first derivative of g is close enough to the first derivative of g evaluated at a. This is true for every positive epsilon. So this is true if we choose a particular value of epsilon, which is 1/2 times the magnitude of the first derivative of g at a. And this, by assumption, is strictly positive. Now let function f be x minus g of x minus z star divided by this constant, the first derivative of g evaluated at a. We want to show that f of x is a contraction in the interval here u from a minus delta to a plus delta. Let's compute the first derivative of f. Because g is differentiable, then f is differentiable. And the first derivative of f is 1 minus the first derivative of g divided by the first derivative of g evaluated at a. The magnitude of the first derivative of f of x, if we choose x to be in this interval, is less than 1/2. By the mean value theorem, let's study f of x minus f of y over x minus y. X and y are in this interval. By the mean value theorem, there exists c between x and y such that f of x minus f of y divided by x minus y is equal to the first derivative of f evaluated at c. Take the magnitude of both sides. X and y are assumed to be distinct. The magnitude of f of x minus f of y is equal to the magnitude of f prime of c times the magnitude of x minus y. Now the first derivative here in magnitude is upper bounded by 1/2. So we have the magnitude of f of x minus f of y is less than or equal to 1/2 the magnitude of x minus y. Before making full use of the contraction mapping theorem, we have here one part of what we need, but we need also to make sure that when the function f is applied to a number in this interval, that what we get is also a number in this interval. So this interval will be like the set big X used at the beginning of this video. Let's investigate the magnitude of f of x minus a. Subtract f of a, add f of a, apply the triangle inequality. So this magnitude is less than or equal to the magnitude of f of x minus f of a plus the magnitude of f of a minus a. Now we know from here that if we choose x and y in this interval, then the magnitude of f of x minus f of y is less than or equal to 1/2, and then the distance between x and y. So this magnitude is upper bounded by 1/2 the magnitude of x minus a. Then here we have f of a minus a. This is how function f is defined. So f of a is equal to a minus g of a minus z star divided by g prime of a. These two guys cancel, and we have this, the magnitude of g of a minus z star divided by the magnitude of g prime of a. Now suppose that we restrict ourselves to choosing z star in the interval from g of a minus eta to g of a plus eta, and eta is epsilon times delta. So let's remind ourselves what is epsilon and delta. Epsilon is chosen to be this positive quantity, 1/2 the magnitude of g prime of a, and delta, this is the separation between x and a that ensures that this magnitude is less than 1/2 of the magnitude of g prime of a. So we will choose eta, we will choose this interval, this neighborhood of g of a, such that eta is 1/2 the magnitude of g prime of a times delta. Now if we do this, then this magnitude here is less than or equal to, because z star is in this interval, so this is less than or equal to eta, and then we have our denominator, which is the magnitude of g prime of a. but eta is chosen to be 1/2 the magnitude of g prime of a times delta. And so this quantity here is upper bounded by delta over 2. This means that the magnitude of f of x minus a is less than or equal to half times delta plus half times delta, that's delta. This means that the value of f of x is indeed between a minus delta to a plus delta. So now f is a contraction mapping in this interval that is called u from a minus delta to a plus delta. And because of this, we know from our theorem that if we carry out those iterations, there will be convergence to a unique point, and this point will be a fixed point of f of x. The fixed point satisfies that x star is equal to f of x star, but f of x star is equal to x star minus g of x star minus z star divided by g prime of a, which is non-zero. If we have this equality, this will go with this, and then we get the g of x star is equal to z star. We have found a solution to the equation g of x is equal to z star.